What if everything you thought you knew about the universe was just the tip of the iceberg? Picture this: the cosmos, vast and infinite, might not be what it seems. Its shape could be anything from a flat sheet to a donut, or even a shape we can't fully comprehend. Welcome to a journey through 30 mind-bending theories about the universe's true shape. From the flat universe supported by the cosmic microwave background to the wild idea of a holographic projection, we're diving into the mysteries that keep scientists up at night. This isn't just about science, it's about the awe-inspiring wonder of existence itself. So, buckle up, because by the end of this video, you'll see the universe in a whole new light. Ready to explore the unknown? Let's go! Now, let's dive into our first theory, the flat universe. Imagine the universe as a vast, endless sheet of paper, stretching out in all directions without any curves or bends. This is the essence of the flat universe theory, one of the most widely accepted ideas in modern cosmology. But how do we know the universe might be flat? The answer lies in the cosmic microwave background, or CMB, which is essentially the afterglow of the Big Bang. Observations of the CMB show that the universe's geometry is remarkably flat, meaning parallel lines will never meet, and the angles of a triangle add up to exactly 180 degrees. This flatness has profound implications. For one, it suggests that the universe will continue expanding forever, rather than collapsing back on itself or slowing down dramatically. It also aligns with the idea that the total energy density of the universe is perfectly balanced, a concept known as the critical density. So, while the idea of a flat universe might sound simple, it's a cornerstone of our understanding of the cosmos, shaping how we think about everything from the Big Bang to the ultimate fate of the universe. And with that, let's move on to our next theory, where things start to get a little more curved. Now, let's take a turn into something a bit more rounded, literally. Our next theory suggests that the universe might not be flat at all, but instead shaped like a sphere. Picture the universe as a giant cosmic balloon, where space curves back on itself in every direction. This is the idea behind the spherical universe theory, also known as a closed universe. In this model, if you were to travel in a straight line for long enough, you'd eventually end up right back where you started, just like circumnavigating the Earth. But what does this mean for the universe's fate? A spherical universe implies that the total energy density is higher than the critical density, which would cause the expansion of the universe to slow down over time. Eventually, gravity would win out, pulling everything back together in what's known as the Big Crunch, a dramatic collapse that could potentially lead to another Big Bang, restarting the cycle all over again. This theory also has fascinating implications for what we might observe in the cosmos. For instance, light traveling through a spherical universe could loop around, creating the possibility of seeing multiple images of the same galaxy or star from different angles. While this idea might sound like science fiction, it's a serious contender in the quest to understand the universe's true shape. And with that, let's move on to our next theory, where the universe takes on a whole new kind of curve. Now, let's stretch our imaginations even further as we explore a universe that curves outward instead of inward. This brings us to the hyperbolic universe theory, also known as an open universe. Imagine space as a giant saddle curving away in every direction. Unlike the spherical universe, where space loops back on itself, a hyperbolic universe would mean that parallel lines would eventually diverge, spreading apart as they travel through space. This kind of curvature suggests that the universe's energy density is lower than the critical density, leading to a very different fate compared to the spherical model. In a hyperbolic universe, the expansion wouldn't just continue, it would accelerate indefinitely, with galaxies drifting farther and farther apart until the cosmos becomes a vast, cold, and empty expanse. This idea aligns with observations of dark energy, the mysterious force driving the universe's accelerated expansion. But what does this mean for the structure of the universe? A hyperbolic shape could create a more complex and intricate cosmic web, with galaxies and clusters arranged in ways that challenge our current understanding. Light traveling through such a universe would follow curved paths, potentially distorting our view of distant objects and creating unique patterns in the cosmic microwave background. While this theory might seem abstract, it offers a fascinating alternative to the flat and spherical models, pushing us to rethink the very fabric of space itself. And with that, let's dive into our next theory, where the universe takes on a shape that's as surprising as it is delicious. Now, let's take a bite out of something truly mind-bending, a universe shaped like a donut. Yes, you heard that right. Welcome to the torus-shaped universe theory, where the cosmos might resemble a giant cosmic donut. In this model, space curves in such a way that it loops back on itself, creating a shape known as a torus. Picture this: if you were to travel in a straight line through this universe, you'd eventually end up right back where you started, just like walking around the surface of a donut. This looping structure could lead to some fascinating cosmic phenomena. For instance, light traveling through a torus-shaped universe might create repeating patterns, making distant galaxies appear multiple times in the sky. Imagine looking up and seeing the same star cluster in different directions. It's like the universe is playing a cosmic game of mirrors. But what does this mean for space-time? A torus topology could imply that the universe is finite but without boundaries, meaning it has a limited volume but no edges. This idea challenges our traditional notions of infinity and could offer new insights into the nature of space and time. Some scientists even suggest that a torus-shaped universe might help explain certain anomalies in the cosmic microwave background, the faint afterglow of the Big Bang. While this theory is still speculative, it opens up a world of possibilities for understanding the universe's true shape. And with that, let's move on to our next theory, where the universe stretches beyond imagination into infinity itself. Now, let's stretch our minds even further as we dive into the idea of an infinite universe. Imagine a cosmos that goes on forever, with no edges, no boundaries, and no end in sight. This is the infinite universe theory, a concept that suggests space is limitless, stretching endlessly in every direction. Unlike the torus-shaped universe we just explored, where space loops back on itself, an infinite universe has no such constraints. It's a vast, unending expanse where the stars, galaxies, and cosmic structures continue infinitely. But how does this idea hold up against what we observe? Interestingly, the infinite universe theory aligns well with one of the key features of our cosmos, cosmic homogeneity. This is the idea that, on the largest scales, the universe looks roughly the same no matter where you are. Whether you're observing from Earth or a galaxy billions of light years away, the distribution of matter and energy appears remarkably uniform. An infinite universe would naturally explain this uniformity, as there's no center or edge to create imbalances. However, an infinite universe also raises some mind-boggling questions. If space truly has no end, does that mean there are infinite versions of Earth, infinite versions of you, and even infinite versions of this very video? While this might sound like science fiction, it's a logical consequence of infinity. In an infinite universe, every possible configuration of matter and energy would exist somewhere, no matter how unlikely. Despite its intriguing implications, the infinite universe theory isn't without its challenges. For one, it's difficult to prove something is truly infinite. Our observations are limited to the observable universe, a finite bubble of space that we can see. Beyond that, we can only speculate. Still, the idea of an infinite universe continues to captivate scientists and dreamers alike, offering a glimpse into the boundless possibilities of existence. And with that, let's shift our focus to another fascinating idea, a universe that's finite but unbounded, where space is limited yet has no edges. How does that work? Let's find out. Now, let's take a step into a universe that's both finite and unbounded, a concept that might sound contradictory at first, but one that offers a fascinating perspective on the cosmos. Imagine a universe that has a limited amount of space, yet no edges or boundaries to define it. This is the finite but unbounded universe theory, a mind-bending idea that challenges our everyday understanding of space and shape. To grasp this concept, think of the surface of a sphere. While the sphere itself is finite in size, its surface has no edges. You could walk in any direction forever without ever hitting a boundary. Now, apply this idea to the universe. In a finite but unbounded universe, space is like the surface of that sphere, but in 3 dimensions. It's a closed, self-contained system where you could theoretically travel in any direction and eventually loop back to your starting point, all without encountering an edge. This theory ties closely to Einstein's theory of general relativity, which describes how massive objects warp the fabric of space-time. According to Einstein, the universe's geometry is shaped by the distribution of matter and energy within it. In a finite but unbounded universe, the curvature of space-time is positive, meaning it bends back on itself, creating a closed, finite structure. This curvature isn't something we can see directly, but it influences how light travels and how galaxies are distributed across the cosmos. One of the most intriguing implications of this theory is its connection to the universe's fate. If the universe is finite but unbounded, its ultimate destiny could be tied to its geometry. A positively curved universe might eventually stop expanding and collapse back in on itself in a big crunch, a dramatic reversal of the Big Bang. Alternatively, if the curvature is just right, the universe could stabilize, avoiding both endless expansion and collapse. But how does this theory hold up against observations? While the cosmic microwave background radiation provides some clues about the universe's geometry, the evidence isn't conclusive. Some measurements suggest the universe is flat, while others hint at a slight positive curvature. This leaves the finite but unbounded universe theory as a compelling possibility, but one that still requires more data to confirm. As we ponder this idea, it's worth noting how it shifts our perspective on the cosmos. A finite but unbounded universe isn't just a scientific concept, it's a reminder of how strange and wondrous reality can be. And with that, let's turn our attention to another intriguing theory, the multiverse, where our universe might be just one of countless others. Now, let's venture into a theory that stretches the boundaries of our imagination, the multiverse. Picture this: our universe, vast and mysterious as it is, might just be one of countless others, each with its own unique set of physical laws and cosmic structures. This is the multiverse theory, a concept that not only redefines our understanding of the universe's shape, but also opens up endless possibilities about its origins. At its core, the multiverse theory suggests that what we perceive as the universe is merely one bubble in an infinite cosmic foam. Each bubble represents a separate universe, potentially with different dimensions, forces, and even fundamental constants. Some of these universes might be flat, others spherical, and some could have shapes we can't even begin to comprehend. The idea is both exhilarating and humbling, as it implies that our universe is just a tiny fragment of a much grander reality. One of the most compelling aspects of the multiverse theory is how it attempts to explain the fine-tuning of our universe. Why do the laws of physics seem so perfectly calibrated to allow for stars, planets, and life? If there are infinite universes, each with different physical parameters, it's statistically inevitable that at least one would have the right conditions for life to emerge. This idea, known as the anthropic principle, offers a potential answer to one of cosmology's biggest questions. But how does the multiverse theory connect to the shape of our universe? If our universe is part of a larger multiverse, its geometry could be influenced by interactions with neighboring universes or by the conditions present at its birth. For instance, some models suggest that collisions between universes could leave imprints on the cosmic microwave background, offering clues about the multiverse's existence. Others propose that the shape of our universe might be a result of quantum fluctuations in a higher dimensional space, where universes are constantly budding off from one another. While the multiverse theory is still speculative, it's supported by several strands of modern physics, including string theory and cosmic inflation. String theory, for example, predicts the existence of extra dimensions that could house other universes, while cosmic inflation suggests that rapid expansion in the early universe could have created pocket universes with varying properties. These ideas, though not yet proven, provide a framework for exploring the multiverse concept. Of course, the multiverse theory isn't without its challenges. Detecting other universes directly is currently beyond our technological capabilities, and some critics argue that the theory is untestable and therefore unscientific. However, proponents counter that indirect evidence, such as anomalies in the cosmic microwave background or unexpected patterns in particle physics, could one day provide support for the multiverse idea. As we ponder the multiverse, it's worth reflecting on what it means for our place in the cosmos. If our universe is just one of many, it shifts our perspective from being the center of existence to being a small part of an unimaginably vast and diverse reality. And with that thought, let's turn our attention to another fascinating theory, the holographic universe, where the very fabric of reality might be a two-dimensional projection. Now, let's shift our gaze to a theory that turns our understanding of reality on its head, the holographic universe. Imagine, if you will, that everything we see, touch, and experience in our three-dimensional world is actually a projection from a two-dimensional surface. This is the essence of the holographic principle, a mind-bending idea that suggests the universe might be more like a hologram than we ever imagined. At its heart, the holographic principle proposes that all the information contained within a volume of space can be represented as data encoded on a boundary to that space. Think of it like a movie projected onto a screen. The three-dimensional images you see are actually created from a flat, two-dimensional surface. In the same way, the holographic principle suggests that our three-dimensional universe could be a projection from a two-dimensional surface, possibly the boundary of the universe itself. This idea has profound implications for our understanding of space-time and quantum gravity. For one, it challenges the traditional view that space-time is smooth and continuous. Instead, it suggests that space-time might be pixelated at the smallest scales, much like a digital image. These pixels of space-time could be the fundamental building blocks of reality, with the universe acting like a giant cosmic computer processing information. The holographic principle also offers a potential solution to one of the biggest puzzles in physics, the black hole information paradox. According to quantum mechanics, information cannot be destroyed, but black holes seem to violate this rule by swallowing information and never letting it escape. The holographic principle suggests that the information swallowed by a black hole isn't lost but is instead encoded on its event horizon, the boundary from which nothing can escape. This idea has sparked a revolution in our understanding of black holes and their role in the universe. But how does this relate to the shape of the universe? If the universe is indeed a hologram, its true shape might not be what we perceive. Instead of a three-dimensional expanse, the universe's fundamental structure could be two-dimensional, with our perception of depth and volume being an illusion. This would mean that the universe's geometry is far more complex than we currently understand, with its true nature hidden in the intricate details of its holographic projection. The holographic principle is supported by various strands of theoretical physics, including string theory and quantum gravity. For instance, string theory suggests that the universe's fundamental particles are actually tiny, vibrating strings, and the holographic principle provides a framework for understanding how these strings interact in a higher dimensional space. Similarly, quantum gravity theories, which aim to reconcile general relativity with quantum mechanics, find the holographic principle to be a promising avenue for explaining the nature of space-time at the smallest scales. Of course, the holographic universe theory is still in its early stages, and much work remains to be done to test its validity. However, it represents a bold and imaginative step forward in our quest to understand the true nature of reality. As we continue to explore this idea, we're reminded that the universe is far stranger and more wondrous than we ever imagined. With that in mind, let's turn our attention to another groundbreaking theory, cosmic inflation, which explores how the universe's rapid expansion in its earliest moments shaped the cosmos we see today. Now, let's zoom back in time to the very beginning of the universe, where another fascinating theory takes center stage, cosmic inflation. This theory proposes that in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion, stretching far faster than the speed of light. This rapid expansion didn't just make the universe bigger, it also left an indelible mark on its geometry and structure. Cosmic inflation helps explain why the universe appears so uniform on large scales. Imagine blowing up a balloon. No matter where you look on its surface, it seems smooth and evenly stretched. Similarly, inflation suggests that the universe's rapid expansion smoothed out any irregularities, creating the remarkably even distribution of matter and energy we observe today. This uniformity is one of the key pieces of evidence supporting the theory. But inflation doesn't just explain the universe's smoothness, it also accounts for the tiny fluctuations that eventually grew into the galaxies, stars, and planets we see today. During inflation, quantum fluctuations, those tiny ripples in the fabric of space-time, were stretched to cosmic scales. These ripples became the seeds for all the structures in the universe, acting like blueprints for the formation of galaxies and clusters of galaxies. Without inflation, it's hard to imagine how such a vast and intricate cosmic web could have formed. One of the most compelling pieces of evidence for cosmic inflation comes from the cosmic microwave background, or CMB, the afterglow of the Big Bang. The CMB shows tiny temperature variations that match the predictions of inflation almost perfectly. These variations are like cosmic fingerprints, revealing the early universe's conditions and supporting the idea that inflation played a crucial role in shaping the cosmos. Inflation also has profound implications for the universe's geometry. According to the theory, the universe's rapid expansion would have flattened its overall shape, much like stretching a crumpled piece of paper smooths out its wrinkles. This aligns with observations suggesting that the universe is flat on large scales, a key prediction of inflation. If the universe weren't flat, the CMB's patterns would look very different, and the distribution of galaxies wouldn't match what we see today. But cosmic inflation isn't just about the past, it also hints at the universe's future. Some models suggest that inflation could still be happening in distant regions of the cosmos, creating pocket universes with different properties. This idea ties into the multiverse concept, where our universe is just one of many, each with its own unique geometry and physical laws. While cosmic inflation is widely accepted, it's not without its challenges. For instance, scientists are still trying to understand what triggered inflation and what caused it to stop. These questions remain at the forefront of cosmology, driving new research and discoveries. As we explore the implications of cosmic inflation, we're reminded of how interconnected the universe's history and structure truly are. From the tiniest quantum fluctuations to the vast cosmic web, inflation provides a framework for understanding the universe's origins and evolution. And with that, let's turn our attention to another intriguing theory, string theory, and its proposal of compactified dimensions, which could further reshape our understanding of the universe's true shape. Now, shifting our focus to a theory that takes us beyond the familiar three dimensions, let's dive into the fascinating world of string theory and its proposal of compactified dimensions. This theory suggests that the universe isn't just made up of the three spatial dimensions we experience: length, width, and height. but also includes additional dimensions that are curled up into incredibly tiny shapes, far too small for us to detect directly. String theory attempts to unify the two great pillars of modern physics: general relativity, which describes the large-scale structure of the universe, and quantum mechanics, which governs the behavior of particles at the smallest scales. To achieve this, string theory introduces the idea that the fundamental building blocks of the universe aren't point-like particles but tiny, vibrating strings. These strings can vibrate in different ways, giving rise to the various particles and forces we observe. But here's where it gets even more intriguing. For the math of string theory to work, it requires extra dimensions, specifically 6 or 7 more, depending on the version of the theory. These extra dimensions aren't sprawling expanses like the ones we're familiar with. Instead, they're compactified, meaning they're curled up into tiny, intricate shapes at every point in space. Imagine a garden hose. From a distance, it looks like a one-dimensional line, but up close, you can see it has a circular cross-section. Similarly, these extra dimensions are hidden in plain sight, folded into shapes so small that they're invisible to us. The geometry of these compactified dimensions isn't arbitrary. It plays a crucial role in determining the properties of the universe. The way these dimensions are shaped influences the vibrations of the strings, which in turn dictate the behavior of particles and forces. For example, the specific geometry of these dimensions could explain why we have the exact number of particles and forces we observe, and why they interact the way they do. In essence, the shape of these hidden dimensions could be the key to understanding the universe's fundamental structure. One of the most exciting implications of compactified dimensions is their potential to explain the universe's overall geometry. If these extra dimensions are curled up in a particular way, they could influence how space-time behaves on larger scales, affecting the universe's curvature and expansion. This means that the shape of the universe we observe, whether it's flat, spherical, or hyperbolic, might be deeply connected to the geometry of these hidden dimensions. While string theory and compactified dimensions offer a compelling framework for understanding the universe, they also present significant challenges. For one, these extra dimensions are so small that they're currently beyond our ability to detect directly. Additionally, string theory is still a work in progress, with many of its predictions yet to be tested experimentally. Despite these hurdles, the theory continues to inspire researchers, offering a tantalizing glimpse into the deeper layers of reality. As we explore the implications of string theory, we're reminded that the universe's true shape might be far more complex and multidimensional than we ever imagined. And with that, let's turn our attention to another groundbreaking idea: the brain world scenario, where our universe could be a membrane floating in a higher dimensional space. Now, let's venture into a theory that takes the idea of extra dimensions even further. The brain world scenario. This model suggests that our entire universe might be a three-dimensional membrane, or brain, floating within a higher dimensional space. Imagine our universe as a slice of bread in a much larger loaf, where the loaf represents the higher dimensional space, often referred to as the bulk. In this framework, everything we know, stars, planets, galaxies, and even ourselves, exists on this brain, while the bulk remains hidden from our direct perception. The brain world scenario emerges from string theory, specifically a branch known as M-theory, which proposes the existence of 11 dimensions. In this model, our three-dimensional universe is just one of many possible brains that could exist within the bulk. These brains can interact with each other, and their dynamics could have profound implications for the shape and behavior of our universe. For instance, collisions between brains could have triggered events like the Big Bang, setting the stage for the universe as we know it. One of the most fascinating aspects of the brain world model is how it could explain some of the mysteries of modern physics. For example, gravity, which is significantly weaker than the other fundamental forces, might appear weak to us because it's not confined to our brain. Instead, it could leak into the higher dimensional bulk, diluting its strength in our observable universe. This idea offers a potential explanation for why gravity behaves so differently compared to the other forces. The shape of our universe in the brain world scenario is also deeply tied to the geometry of the bulk. If the bulk has a specific curvature or structure, it could influence how our brain behaves, affecting everything from the expansion rate of the universe to the distribution of matter and energy. Some theories even suggest that the bulk could contain other brains, each hosting its own universe with different physical laws. This opens up the possibility of a multiverse, where countless universes coexist in the same higher dimensional space. However, like many cutting-edge theories, the brain world scenario faces challenges. Detecting evidence of higher dimensions or other brains is incredibly difficult, as their effects would be subtle and hard to observe directly. Despite this, the model continues to inspire researchers, offering a bold new perspective on the nature of reality and the universe's true shape. As we ponder the implications of the brain world scenario, we're reminded that the universe might be far more intricate and interconnected than we've ever imagined. And with that, let's turn our attention to another captivating idea, the cyclic universe theory, where the cosmos undergoes endless cycles of expansion and contraction. Now, let's shift our focus to a theory that imagines the universe as a cosmic pendulum, swinging endlessly between expansion and contraction, the cyclic universe theory. This idea proposes that our universe isn't a one-time event but part of an infinite series of cycles, each beginning with a big bang and ending with a big crunch, only to start anew. Picture the universe as a giant accordion, expanding and contracting in a rhythmic dance that repeats over and over again. In this model, each cycle begins with a rapid expansion, much like the one we observe today, where galaxies and structures form and evolve. But instead of continuing to expand forever, the universe eventually slows down, reverses course, and collapses back into an incredibly dense state. This collapse, known as the Big Crunch, sets the stage for the next Big Bang, creating a new cycle of expansion. The process repeats indefinitely, with each cycle leaving its mark on the universe's shape and structure. One of the most intriguing aspects of the cyclic universe theory is how it addresses the question of the universe's ultimate fate. Unlike models that predict an endless expansion leading to a cold, dark void, or a collapse into a singularity, the cyclic universe offers a middle ground, a universe that never truly ends but instead reinvents itself over and over. This cyclical nature could also explain certain features of our universe, such as the uniformity of the cosmic microwave background radiation, which might carry imprints from previous cycles. The shape of the universe in this model is deeply influenced by these cycles. Each expansion and contraction could stretch, twist, or reshape the fabric of space-time, leaving behind a unique geometric signature. Over countless cycles, the universe might develop a complex, layered structure, with each cycle building on the remnants of the last. Some versions of the theory even suggest that the universe's shape could evolve over time, becoming more intricate with each new cycle. However, the cyclic universe theory isn't without its challenges. For one, it requires a mechanism to reset the universe after each big crunch, ensuring that the next cycle begins with a clean slate. Additionally, detecting evidence of previous cycles is incredibly difficult, as the intense heat and density of the Big Crunch would likely erase most traces of the past. Despite these hurdles, the theory remains a compelling alternative to the standard Big Bang model, offering a vision of the universe that is both eternal and ever-changing. As we reflect on the cyclic universe, we're reminded that the cosmos might not have a single, definitive shape, but rather a dynamic, evolving form that transforms with each cycle. And with that, let's turn our attention to another fascinating idea, the bubble universe theory, where our universe is just one of many bubbles in a vast cosmic foam. Now, let's dive into a theory that paints the cosmos as a frothy sea of possibilities, the bubble universe theory. imagine our universe not as a solitary entity, but as one of countless bubbles floating in an infinite cosmic foam. Each bubble represents a separate universe with its own unique laws of physics, dimensions, and even time. This idea, rooted in the concept of eternal inflation, suggests that the fabric of space-time is constantly expanding, giving rise to new universes like bubbles forming in a boiling pot. In this model, our universe is just one bubble among many, each born from a quantum fluctuation in the fabric of space-time. As these bubbles grow, they can collide, merge, or drift apart, creating a vast multiverse where every possible configuration of reality exists. This means that somewhere out there could be a universe where gravity is stronger, or one where time flows backward. The bubble universe theory opens up a mind-bending array of possibilities, challenging our understanding of what it means to exist. One of the most fascinating aspects of this theory is how it redefines the shape of our universe. Instead of being a single, continuous expanse, our universe might be a finite bubble with its own boundaries, floating in a higher dimensional space. These boundaries could be invisible to us, much like the surface of a soap bubble is nearly invisible to the naked eye. Yet, they could still influence the way our universe evolves, shaping its structure and even its ultimate fate. The bubble universe theory also offers a potential explanation for some of the mysteries of cosmology. For instance, the uniformity of the cosmic microwave background radiation could be the result of our bubble universe forming in a region of space that was already smooth and uniform. Similarly, the accelerated expansion of our universe might be influenced by the pressure of neighboring bubbles in the cosmic foam, pushing against our own. However, like all theories, the bubble universe model comes with its own set of challenges. Detecting evidence of other bubbles is incredibly difficult, as they would exist beyond the observable limits of our universe. Additionally, the idea of a multiverse raises philosophical questions about the nature of reality and our place within it. Are we just one of an infinite number of possibilities, or is there something special about our particular bubble? As we ponder the bubble universe theory, we're reminded that the cosmos might be far more complex and interconnected than we ever imagined. And with that, let's turn our attention to another intriguing idea: conformal cyclic cosmology, where the universe undergoes infinite cycles of rebirth and renewal. Now, let's explore a theory that reimagines the universe as a never-ending loop of creation and destruction. Conformal cyclic cosmology. Proposed by the renowned physicist Roger Penrose, this theory suggests that the universe doesn't have a single beginning or end. Instead, it goes through infinite cycles, each one a rebirth of the cosmos. In this model, the universe expands, cools, and eventually fades into a state of near-nothingness, only to be reborn in a new Big Bang, starting the cycle all over again. At the heart of this idea is the concept of conformal geometry, which allows the universe to transition smoothly from one cycle to the next. Penrose argues that as the universe reaches the end of its current cycle, all matter and energy decay into massless particles like photons. At this point, the universe becomes so vast and empty that it effectively resets its scale, making it indistinguishable from the conditions of the next Big Bang. This resetting process is what allows the cycles to repeat endlessly, with no loss of information or structure. One of the most striking implications of conformal cyclic cosmology is its challenge to the traditional idea of a linear timeline. Instead of a universe with a clear beginning and end, we have a cosmos that exists in a perpetual state of renewal. This raises fascinating questions about the nature of time itself. Is time truly linear, or is it cyclical, looping back on itself in an eternal dance of creation and destruction? Penrose's theory also offers a potential explanation for some of the mysteries in the cosmic microwave background radiation. He suggests that certain patterns in the CMB could be remnants of gravitational waves from previous cycles, acting as cosmic echoes of universes long gone. If proven, this would provide compelling evidence for the cyclical nature of the universe and reshape our understanding of its geometry. However, conformal cyclic cosmology is not without its critics. Some argue that the theory relies on assumptions that are difficult to test, such as the idea that information can be preserved across cycles. Others question whether the universe could truly reset itself in the way Penrose describes. Despite these challenges, the theory remains a bold and imaginative attempt to answer one of the deepest questions in cosmology: what is the ultimate fate of the universe? As we reflect on the idea of an endlessly cycling cosmos, we're reminded that the universe might be far more dynamic and interconnected than we ever imagined. And with that, let's turn our attention to another fascinating concept: quantum foam, where the fabric of space-time itself becomes turbulent at the smallest scales. Now, let's dive into the fascinating world of quantum foam, a concept that takes us to the very edge of our understanding of space and time. Imagine zooming in on the fabric of the universe, past galaxies, stars, and even atoms, until you reach the smallest possible scales. Here, space-time isn't smooth and continuous as we often picture it. Instead, it's a seething, turbulent sea of fluctuations, what physicists call quantum foam. At these incredibly tiny scales, the rules of classical physics break down and quantum mechanics takes over. Space-time becomes a chaotic, ever-changing landscape with tiny bubbles of energy popping in and out of existence. These fluctuations are so small that they're measured in units called Planck lengths, which are about 1/1,000,000,000 of a trillionth of the size of an atom. To put it simply, quantum foam is the universe's way of showing that even the fabric of reality has a kind of graininess at its most fundamental level. But how does this chaotic, frothy nature of space-time affect the universe's overall shape? One possibility is that quantum foam could create tiny ripples or distortions in the geometry of space-time. Over vast distances, these ripples might add up, influencing the large-scale structure of the universe. Some theories even suggest that quantum foam could play a role in the formation of cosmic structures like galaxies and galaxy clusters, acting as the seeds from which these massive objects grow. Another intriguing idea is that quantum foam might hold clues to the unification of general relativity and quantum mechanics, two of the most successful but seemingly incompatible theories in physics. General relativity describes the universe on large scales, where gravity shapes the cosmos, while quantum mechanics governs the behavior of particles at the smallest scales. Quantum foam sits at the intersection of these two worlds, offering a potential bridge between them. If we can understand how space-time behaves at this level, we might finally uncover the true nature of the universe's geometry. Of course, studying quantum foam is no easy task. Its effects are so minuscule that they're nearly impossible to observe directly with current technology. However, scientists are exploring indirect ways to detect its influence, such as by studying the behavior of particles or looking for subtle anomalies in the cosmic microwave background. These efforts could one day reveal whether quantum foam is just a theoretical curiosity or a fundamental feature of the universe's structure. As we ponder the turbulent, frothy nature of space-time, we're reminded that the universe is full of surprises, even at the smallest scales. And with that, let's turn our attention to another mind-bending idea: the possibility that our universe exists inside a black hole, a theory that redefines our understanding of space and time. Now, let's venture into one of the most mind-bending theories about the universe's shape: the idea that our entire cosmos might exist inside a black hole. This concept, known as black hole cosmology, flips our understanding of space and time on its head, suggesting that what we perceive as the universe could be the interior of a massive black hole. To grasp this theory, let's start with what we know about black holes. These mysterious objects are regions of space where gravity is so intense that nothing, not even light, can escape. They're often thought of as cosmic vacuum cleaners, sucking in everything around them. But what if, instead of being destructive, a black hole could be the birthplace of an entirely new universe? According to black hole cosmology, when matter collapses into a black hole, it doesn't just disappear into a singularity, a point of infinite density. Instead, the extreme conditions inside the black hole could trigger the creation of a new universe with its own space-time and physical laws. In this scenario, our universe might be the result of such an event, born from the collapse of matter in a parent universe. This theory also offers a fascinating explanation for the Big Bang. Instead of the universe starting from a single point of infinite density, the Big Bang could have been the moment when matter from a black hole in another universe began expanding into a new space-time. In other words, the Big Bang might not have been the beginning of everything, but rather a transition point between universes. But how does this idea affect our understanding of the universe's shape? If we're inside a black hole, the geometry of our universe could be shaped by the intense gravitational forces at play. Some models suggest that the universe might have a closed, spherical shape, curving back on itself due to the black hole's influence. Others propose that the universe could be infinite, stretching endlessly within the confines of the black hole's event horizon. One of the most intriguing aspects of black hole cosmology is how it bridges the gap between the very large and the very small. Black holes are governed by the laws of general relativity, which describe the universe on cosmic scales, but their interiors might be dominated by quantum effects. This could provide a unique opportunity to explore how gravity and quantum mechanics interact, potentially leading to a unified theory of physics. Of course, this theory is still highly speculative, and there's no direct evidence to prove that our universe exists inside a black hole. However, it offers a compelling way to think about the origins and structure of the cosmos, challenging us to reconsider what we know about space, time, and the nature of reality itself. As we ponder the possibility of living inside a black hole, let's shift our focus to another captivating idea: the fractal universe, where the structure of the cosmos repeats itself at different scales, creating a mesmerizing pattern that stretches across the universe. Now let's dive into a theory that paints the universe as a breathtaking work of art: the fractal universe. Imagine looking at a snowflake under a microscope and seeing its intricate patterns repeat at smaller and smaller scales. The fractal universe theory suggests that the cosmos itself might operate in a similar way, with its structure repeating across different levels of scale, from the tiniest particles to the vastness of galaxies. At its core, a fractal is a geometric pattern that repeats itself infinitely, no matter how much you zoom in or out. Think of a tree where each branch splits into smaller branches, and those split into even smaller ones, all following a similar pattern. The fractal universe theory proposes that the universe might be built in this same recursive way, with its large-scale structures, like galaxy clusters and superclusters, mirroring the patterns of smaller structures, such as individual galaxies or even the distribution of matter within them. This idea isn't just visually stunning, it has profound implications for our understanding of cosmic geometry. If the universe is fractal, it challenges the traditional view of a smooth, uniform cosmos. Instead, it suggests that the universe is inherently uneven, with patterns of matter and energy repeating across scales. This could mean that the distribution of galaxies isn't random but follows a specific, self-similar blueprint. One of the most fascinating aspects of this theory is how it connects the very large to the very small. For example, the way galaxies cluster together might resemble the way atoms arrange themselves in a crystal. This repetition of patterns could hint at underlying laws of physics that operate consistently across all scales, offering a new way to think about the universe's structure and evolution. However, the fractal universe theory isn't without its challenges. Observations of the cosmic microwave background, the afterglow of the Big Bangs, suggest that the universe is largely homogeneous on the largest scales, which seems to contradict the idea of a fractal structure. But some researchers argue that the fractal pattern might only become apparent at smaller scales, leaving room for debate and further exploration. What makes this theory so captivating is its ability to blend art and science. It invites us to see the universe not just as a collection of random objects, but as a grand, interconnected design where every part reflects the whole. Whether or not the fractal universe theory holds up to scrutiny, it reminds us that the cosmos is full of patterns waiting to be discovered, and that sometimes the most profound truths are hidden in the details. As we marvel at the idea of a fractal universe, let's turn our attention to another cosmic mystery, the so-called axis of evil, an anomaly in the cosmic microwave background that challenges our understanding of the universe's shape and symmetry. Now, let's shift our focus to one of the most puzzling anomalies in cosmology, the so-called axis of evil. This mysterious feature in the cosmic microwave background, or CMB, has left scientists scratching their heads and questioning some of our most fundamental assumptions about the universe's shape and symmetry. The CMB is essentially the oldest light in the universe, a faint glow left over from the Big Bang. It provides a snapshot of the early universe, and for the most part, it appears remarkably uniform, supporting the idea that the cosmos is isotropic, meaning it looks the same in all directions. But here's where things get interesting. When researchers analyzed the CMB in greater detail, they noticed something odd, a strange alignment of temperature fluctuations that seemed to point in a specific direction, almost as if the universe had a preferred axis. This unexpected pattern was dubbed the axis of evil, a name that reflects both its puzzling nature and its potential to disrupt our understanding of cosmic geometry. So, what exactly does this anomaly mean? If the universe is truly isotropic, we wouldn't expect to see any preferred direction or alignment in the CMB. Yet the axis of evil suggests that there might be some kind of asymmetry or structure on the largest scales, challenging the idea of a perfectly uniform cosmos. Some scientists have proposed that this could hint at a deeper, underlying geometry to the universe, one that we don't yet fully understand. Others have speculated that it might be evidence of something even more profound, like the influence of another universe beyond our own. Of course, not everyone is convinced. Some researchers argue that the axis of evil could simply be a statistical fluke or an artifact of the way we process CMB data. After all, the universe is vast, and sometimes patterns can emerge purely by chance. But the fact that this anomaly persists across multiple observations makes it hard to dismiss entirely. It's a reminder that even our most precise measurements can still leave room for mystery and debate. What makes the axis of evil so intriguing is its potential to reshape our understanding of the universe's shape and structure. If it's real, it could mean that the cosmos isn't as uniform as we once thought, opening the door to new theories about its origins and evolution. It's a reminder that the universe is full of surprises, and that even the most well-established ideas can be challenged by a single, unexplained anomaly. As we ponder the implications of the axis of evil, let's turn our attention to another fascinating aspect of cosmic geometry, the role of topology in shaping the universe's overall structure. Now, let's dive into the intriguing world of cosmic topology, where the universe's shape isn't just about its local geometry, but also its global structure. Imagine the universe as a vast cosmic puzzle, where the way space is connected on the largest scales could hold the key to understanding its true form. This is where topology comes into play, a branch of mathematics that studies the properties of space that remain unchanged, even when that space is stretched or twisted. In the context of cosmology, topology explores how the universe might be shaped on a global level. For instance, could the universe be finite but still have no edges like the surface of a sphere? Or might it have a more complex structure, such as a torus, where space loops back on itself in multiple directions? These possibilities aren't just abstract ideas, they could have real implications for how we interpret observations like the cosmic microwave background, or CMB. Take the CMB, for example. If the universe has a specific topological shape, it could leave subtle fingerprints in the CMB's temperature fluctuations. Imagine looking at a pattern on a balloon. If you stretch or twist the balloon, the pattern changes in predictable ways. Similarly, if the universe has a particular topology, it could create repeating patterns or anomalies in the CMB that we might detect. This is why cosmic topology is such a powerful tool. It allows us to test ideas about the universe's shape by looking for these telltale signs in the oldest light we can observe. One fascinating possibility is that the universe could be a multiply-connected space, meaning it has a finite volume but no boundaries. Think of it like a video game world where if you travel far enough in one direction, you end up back where you started. This kind of topology could explain certain features in the CMB, such as the mysterious axis of evil we discussed earlier. If the universe is shaped in a way that creates repeating patterns, it might help us make sense of why some anomalies appear to align in specific directions. Of course, cosmic topology isn't just about solving puzzles. It's also about expanding our understanding of the universe's origins and evolution. If we can determine the universe's global shape, it could shed light on how it formed, how it's expanding, and even what its ultimate fate might be. It's a reminder that the cosmos is more than just a collection of stars and galaxies. It's a dynamic, interconnected system with a geometry that might be far more complex than we ever imagined. As we explore these ideas, it's worth noting that cosmic topology isn't just a theoretical exercise. It's a field that's constantly evolving, driven by new observations and advancements in technology. With each discovery, we get closer to unraveling the mysteries of the universe's shape and structure. And who knows, the answers might be hiding in the very fabric of space itself, waiting for us to piece them together. With that in mind, let's turn our attention to another captivating theory that challenges our understanding of the cosmos: the Hyperbolic Universe model, where the universe's shape is shaped by colliding brains. Now, shifting our gaze to another groundbreaking idea, let's explore the Hyperbolic Universe model. This theory proposes a dramatic origin story for our cosmos, one where the universe's shape and structure are shaped by the collision of higher dimensional objects known as brains. Picture this: our universe isn't just floating in empty space, it's part of a much larger, multidimensional reality. In this model, the universe we inhabit is a three-dimensional brain, a kind of membrane, existing alongside other brains in a higher dimensional space. The Hyperbolic model suggests that the Big Bang wasn't the beginning of everything, but rather the result of a collision between two of these brains. Imagine two sheets of paper floating in a vast, unseen dimension, slowly moving toward each other until they crash. That collision would release an enormous amount of energy, sparking the expansion of our universe as we know it. This idea challenges the traditional view of the Big Bang as a singular, explosive event, offering instead a cyclical narrative where the universe undergoes repeated collisions and rebirth. What's fascinating about this model is how it redefines the universe's shape and evolution. If the Hyperbolic scenario is correct, the universe's geometry could be influenced by the dynamics of these brain collisions. For instance, the way the brains interact, whether they collide head-on or graze each other, could determine the distribution of matter and energy in the early universe, shaping its large-scale structure. This could even explain why the universe appears so uniform on the largest scales, a feature that has puzzled cosmologists for decades, but the implications don't stop there. The Hyperbolic model also offers a potential solution to the problem of cosmic inflation. While inflation theory suggests that the universe underwent a rapid expansion shortly after the Big Bang, the Hyperbolic model proposes that the smoothness and uniformity of the cosmos could instead be the result of these brain collisions. This alternative explanation opens up new avenues for understanding the universe's origins and its ultimate fate. Of course, like any bold theory, the ekpyrotic model comes with its own set of challenges. Detecting evidence of higher dimensional brains or the remnants of these collisions is no easy task. Yet, the idea continues to inspire researchers, pushing the boundaries of what we know about the universe's shape and history. It's a reminder that the cosmos is full of surprises, and sometimes the most extraordinary explanations lie just beyond the limits of our current understanding. As we ponder the ekpyrotic universe, it's worth considering how this theory connects to the broader tapestry of cosmological ideas. From the Big Bang to cosmic inflation, and now to colliding brains, each model offers a unique lens through which to view the universe's true shape. And as we continue to explore these possibilities, we inch closer to uncovering the profound mysteries that define our existence. With that, let's turn our attention to another fascinating concept, the simulated universe hypothesis, where the very fabric of reality might be a product of advanced computation. Now, stepping into the realm of the extraordinary, let's explore the simulated universe hypothesis. This theory proposes a mind-bending idea. What if our universe, with all its galaxies, stars, and planets, isn't a physical reality but rather an incredibly advanced simulation? Imagine a civilization so technologically advanced that they could create a virtual cosmos, complete with its own laws of physics, history, and even conscious beings. This isn't science fiction, it's a serious scientific and philosophical debate that challenges our understanding of reality itself. At the heart of this hypothesis is the idea that the universe's shape and structure might not be governed by natural laws but by the rules of a computational program. Think of it like a video game where every detail, from the movement of particles to the formation of galaxies, is coded into the system. In this scenario, the universe's geometry could be a product of the simulation's design, shaped by the algorithms that define how space and time behave. One of the most compelling arguments for this theory comes from the rapid advancement of technology. If humanity can already create immersive virtual worlds, it's not far-fetched to imagine a future civilization capable of simulating an entire universe. Some scientists even suggest that if such simulations are possible, the odds are high that we're living in one. After all, if there are countless simulated universes, the likelihood of being in the original reality becomes vanishingly small. But the implications go beyond science. They touch on deep philosophical questions. If the universe is a simulation, what does that mean for free will, consciousness, and the nature of existence? Are we merely characters in a cosmic game, or do we have the power to shape our own destiny within the simulation? These questions blur the line between science and philosophy, inviting us to rethink what it means to be real. Critics of the simulated universe hypothesis point out the lack of direct evidence. How could we ever prove that we're living in a simulation? Some researchers suggest looking for glitches or patterns in the fabric of reality, tiny errors in the code that might reveal the simulation's artificial nature. Others argue that the hypothesis is untestable, making it more of a thought experiment than a scientific theory. Yet, the idea continues to captivate scientists and thinkers alike. It challenges us to question our assumptions about the universe's shape and origins, pushing the boundaries of what we consider possible. Whether or not the simulated universe hypothesis holds water, it serves as a powerful reminder that reality might be far stranger than we imagine. As we reflect on this theory, it's worth considering how it connects to the broader exploration of the universe's true shape. From colliding brains to simulated realities, each idea offers a unique perspective on the cosmos, inviting us to see the universe in a new light. And as we continue to probe these mysteries, we may find that the answers lie not just in the stars, but in the very nature of existence itself. With that, let's turn our attention to another intriguing concept, the mirror universe, where our cosmos might have a hidden twin, shaping the universe's geometry in ways we're only beginning to understand. Now, shifting our gaze to a concept that feels like it's straight out of science fiction, let's dive into the mirror universe theory. This idea suggests that our universe might not be alone. It could have a hidden twin, a parallel cosmos that mirrors our own in ways we're only beginning to understand. Imagine a universe that's almost identical to ours, but with subtle differences that could reshape everything we know about space, time, and the very fabric of reality. At the heart of this theory is the idea of symmetry. Just as a mirror reflects an image, the mirror universe would reflect the structure and properties of our own cosmos. But here's where it gets fascinating. This mirror universe wouldn't just be a carbon copy. It could have its own unique laws of physics, particles, and even dimensions that interact with ours in ways we can't yet detect. Some scientists propose that this hidden twin could explain mysteries like dark matter, suggesting that what we perceive as invisible matter might actually be the gravitational influence of the mirror universe leaking into our own. One of the most intriguing aspects of this theory is how it could influence the universe's overall geometry. If our universe and its mirror twin are intertwined, their combined gravitational effects could create a complex, interconnected shape. Picture two sheets of paper pressed together, each representing a universe. The way they interact could warp the fabric of space-time, creating a geometry that's far more intricate than we currently understand. But how could we ever detect a mirror universe? Some researchers suggest looking for anomalies in the cosmic microwave background, the faint afterglow of the Big Bang. If the mirror universe exists, its presence might leave subtle imprints in this ancient light, like faint echoes of a hidden twin. Others propose that particle physics experiments could uncover evidence of mirror particles, which would interact with our universe in ways that defy our current understanding of physics. Of course, the mirror universe theory isn't without its challenges. Critics argue that it's difficult to test, as the mirror universe would, by definition, be nearly invisible to us. Yet, the idea continues to captivate scientists and thinkers, offering a tantalizing glimpse into what might lie beyond the boundaries of our observable cosmos. As we ponder this theory, it's worth considering how it connects to the broader quest to understand the universe's true shape. From simulated realities to hidden twins, each idea pushes the boundaries of our imagination, inviting us to see the cosmos in a new light. And as we continue to explore these mysteries, we may find that the universe's geometry is far more complex and far more beautiful than we ever imagined. With that, let's turn our attention to another fascinating concept, the idea of time as a dimension, and how treating it as a spatial dimension could reshape our understanding of the universe's shape. Now, let's take a step into a realm where time itself becomes something far more tangible, a dimension we can almost touch. The idea of time as a spatial dimension might sound like something out of a science fiction novel, but it's a concept that has fascinated physicists for decades. What if time isn't just a linear progression from past to future, but a dimension that we can move through, just like we move through space? In our everyday lives, we think of time as a one-way street, always moving forward. But in the realm of theoretical physics, time is often treated as the fourth dimension, alongside the three spatial dimensions of length, width, and height. This idea forms the backbone of Einstein's theory of relativity, where space and time are woven together into a single fabric called space-time. Imagine space-time as a giant grid, where every event in the universe has a specific location, not just in space, but in time as well. Now, here's where things get really interesting. If time is a dimension, could the universe's shape be influenced by how time interacts with space? Some theories suggest that the universe might have a more complex geometry than we currently understand, with time acting as a kind of curved dimension. Picture a sheet of paper bending under its own weight, except instead of paper, it's the fabric of space-time itself. This curvature could create shapes and structures that are impossible to visualize in our three-dimensional world, but might hold the key to understanding the universe's true form. One of the most intriguing implications of this idea is the possibility of time loops or closed time-like curves. In a universe where time is a spatial dimension, it's theoretically possible for time to fold back on itself, creating loops where events repeat or even where the past and future intersect. While this might sound like the stuff of time travel fantasies, it's a serious area of study in physics, with implications for everything from black holes to the origins of the universe. But how does this reshape our understanding of the universe's shape? If time is a dimension, then the universe isn't just a static object, it's a dynamic, ever-changing entity. Its shape could evolve over time, influenced by the interplay between space and time. Some models even suggest that the universe might have a shape that extends beyond our three-dimensional perception, with time adding an extra layer of complexity to its geometry. Of course, treating time as a spatial dimension isn't without its challenges. It forces us to rethink fundamental concepts like cause and effect, and it raises questions about the nature of reality itself. Yet, it's a theory that continues to inspire scientists, offering a new lens through which to view the cosmos. As we explore this idea, it's worth reflecting on how it connects to the broader quest to understand the universe's true shape. From mirror universes to time as a dimension, each theory pushes the boundaries of our imagination, inviting us to see the cosmos in a new light. And as we continue to unravel these mysteries, we may find that the universe's geometry is far more intricate and far more wondrous than we ever imagined. With that, let's turn our attention to another fascinating concept: the role of non-Euclidean geometry in shaping our understanding of the universe. Now, let's shift our perspective to a concept that turns our everyday understanding of space on its head: non-Euclidean geometry. For centuries, Euclidean geometry, the geometry we learn in school, has shaped how we think about shapes, angles, and distances. It's based on the idea that space is flat, with parallel lines never meeting and the angles of a triangle always adding up to 180 degrees. But what if space isn't flat? What if it bends, twists, or curves in ways that defy these familiar rules? That's where non-Euclidean geometry comes in. Non-Euclidean geometry challenges the very foundation of how we perceive space. Instead of assuming a flat, unchanging plane, it explores the possibilities of curved space. There are two main types of non-Euclidean geometry: hyperbolic and spherical. In hyperbolic geometry, space curves outward like the surface of a saddle, causing parallel lines to diverge and triangles to have angles that add up to less than 180 degrees. In spherical geometry, space curves inward like the surface of a sphere, where parallel lines eventually meet and triangles have angles that sum to more than 180 degrees. So, how does this relate to the universe's shape? If the universe isn't flat, as some observations suggest, then non-Euclidean geometry could hold the key to understanding its true form. For instance, if the universe is hyperbolic, it would mean space is expanding faster than we thought, with a geometry that stretches outward in all directions. On the other hand, a spherical universe would imply that space is finite and eventually curves back on itself, creating a closed, bounded cosmos. This idea isn't just theoretical, it has real implications for how we interpret cosmic phenomena. For example, the way light travels through the universe can be affected by the curvature of space. If the universe is non-Euclidean, light might follow paths that bend or twist, creating effects like gravitational lensing, where massive objects distort the light from distant stars and galaxies. These observations could provide clues about the universe's overall geometry. But non-Euclidean geometry doesn't just challenge our understanding of space, it also reshapes how we think about the universe's origins and fate. A hyperbolic universe might continue expanding forever, while a spherical universe could eventually collapse back in on itself. These possibilities force us to reconsider not just the shape of the cosmos, but also its ultimate destiny. As we explore these ideas, it's clear that non-Euclidean geometry offers a powerful tool for unraveling the mysteries of the universe's shape. By stepping outside the flat, predictable world of Euclidean geometry, we open ourselves to a cosmos that's far more dynamic, complex, and awe-inspiring than we ever imagined. With that in mind, let's move on to another fascinating concept: the role of cosmic strings in shaping the universe's geometry. Now, let's dive into a concept that sounds like it's straight out of science fiction, but could hold the key to understanding the universe's shape: cosmic strings. Imagine the fabric of space-time as a vast, intricate tapestry. Cosmic strings are like tiny, invisible threads woven into this tapestry, hypothetical one-dimensional defects in space-time that could have formed in the early universe. These strings are thought to be incredibly thin but unimaginably dense, stretching across vast cosmic distances. So, what makes cosmic strings so fascinating? For starters, they're not just theoretical curiosities, they could have real, observable effects on the universe's geometry. If cosmic strings exist, their immense gravitational pull could warp space-time, creating ripples that influence the paths of light and matter. This warping could leave behind distinct signatures, such as double images of distant galaxies or unusual patterns in the cosmic microwave background. But how do cosmic strings form? Scientists believe they could have emerged during the universe's infancy, a fraction of a second after the Big Bang. As the universe expanded and cooled, phase transitions similar to water freezing into ice may have created these one-dimensional defects. Think of it like cracks forming in ice as it freezes, but on a cosmic scale. These cracks or cosmic strings would then stretch and evolve as the universe continued to expand. The implications of cosmic strings for the universe's shape are profound. If they exist, they could act as cosmic scaffolding, shaping the large-scale structure of the universe. Their gravitational effects might also help explain some of the anomalies we observe, like the uneven distribution of galaxies or the mysterious dark matter that seems to hold the cosmos together. What's even more intriguing is that cosmic strings could provide a window into the universe's earliest moments. By studying their potential effects, scientists might uncover clues about the conditions that existed just after the Big Bang. This could help us piece together not just the universe's shape, but also its origins and evolution. While cosmic strings remain hypothetical for now, their study pushes the boundaries of our understanding of space, time, and the universe itself. They remind us that the cosmos is full of surprises, and that even the tiniest threads could hold the answers to some of our biggest questions. With that in mind, let's turn our attention to another force shaping the universe: dark energy, and its role in determining the cosmos's ultimate fate. Now, let's shift our focus to one of the most mysterious forces in the cosmos: dark energy. While cosmic strings might shape the universe on a smaller scale, dark energy plays a far more sweeping role in determining the universe's overall geometry and ultimate fate. Dark energy is the name scientists have given to the mysterious force driving the accelerated expansion of the universe. Unlike gravity, which pulls things together, dark energy seems to push space itself apart. This strange behavior was first discovered in the late 1990s when astronomers observed that distant supernovae were fainter than expected, suggesting the universe was expanding faster than previously thought. So, how does dark energy influence the universe's shape? To understand this, we need to look at the relationship between the universe's expansion and its geometry. If dark energy continues to dominate, it could lead to a flat universe that expands forever, growing colder and more diffuse over time. In this scenario, galaxies would drift farther apart, and the universe would become increasingly empty. But dark energy's influence doesn't stop there. It also plays a crucial role in determining the universe's ultimate fate. One possibility is the Big Freeze, where dark energy causes the universe to expand so rapidly that all matter and energy become too spread out to interact. Another, more dramatic scenario is the Big Rip, where dark energy's strength increases over time, eventually tearing apart galaxies, stars, and even atoms themselves. Interestingly, dark energy's effects aren't just about the future, they also shape the universe's past and present. By studying how dark energy influences the rate of expansion, scientists can learn more about the universe's early conditions and how it evolved into the structure we see today. For example, dark energy's presence helps explain why the universe appears so uniform on large scales, a phenomenon known as cosmic homogeneity. Despite its profound impact, dark energy remains one of the greatest mysteries in modern cosmology. We don't yet know what it is or where it comes from, but its effects are undeniable. Some theories suggest dark energy could be a property of space itself, while others propose its link to new, undiscovered particles or fields. What's clear is that dark energy holds the key to understanding not just the universe's shape, but its destiny. As we continue to study this enigmatic force, we may uncover answers to some of the most fundamental questions about the cosmos. How did it begin? How will it end? And what does it all mean for the fabric of reality itself? With dark energy shaping the universe on such a grand scale, it's time to explore another fascinating concept that could redefine our understanding of space-time: wormholes and their potential impact on the universe's geometry. Now, let's dive into a concept that sounds like it's straight out of science fiction, but has serious scientific implications: wormholes. These theoretical tunnels in space-time have long captured the imagination of both scientists and storytellers, but they also hold fascinating possibilities for understanding the universe's shape and connectivity. A wormhole, often referred to as an Einstein-Rosen bridge, is a hypothetical shortcut through space-time that could connect two distant points in the universe. Imagine folding a piece of paper so that two far apart dots touch. This is essentially how a wormhole would work, creating a bridge that bypasses the vast distances of space. While wormholes remain purely theoretical, their existence could dramatically alter our understanding of the universe's geometry. If wormholes exist, they could create a kind of cosmic network, linking different regions of the universe in ways that defy traditional notions of distance and shape. For example, a wormhole could connect two galaxies that appear billions of light-years apart, effectively making them neighbors. This would mean the universe's geometry isn't just about the curvature of space, but also about how these tunnels could warp and connect it in unexpected ways. But how would wormholes influence the universe's overall shape? One possibility is that they could create a more complex, interconnected structure, where space-time isn't just a smooth, continuous fabric, but a web of shortcuts and pathways. This could challenge our current understanding of the universe as a single, unified expanse and suggest that it might have a more intricate, multi-layered geometry. Interestingly, wormholes could also have implications for the universe's fate. If they exist, they might provide a way for matter and energy to travel across vast distances, potentially influencing how the universe evolves over time. For instance, if wormholes allowed galaxies to exchange material, it could slow down the process of cosmic expansion or even create new pathways for star formation in otherwise isolated regions. Of course, wormholes come with their own set of challenges. For one, they would require exotic forms of matter with negative energy to remain stable, something we've yet to discover. Additionally, the extreme gravitational forces near a wormhole's entrance could make them incredibly dangerous to approach, let alone traverse. Despite these hurdles, the idea of wormholes continues to inspire both scientific inquiry and creative speculation. They remind us that the universe's shape might be far more complex and interconnected than we currently imagine. As we explore these possibilities, we're not just uncovering new ways to think about space-time, we're also opening doors to questions about the very nature of reality. With wormholes offering such intriguing possibilities for the universe's geometry, it's time to turn our attention to another groundbreaking idea: how quantum gravity theories attempt to reconcile the universe's shape at the smallest and largest scales. Now, let's shift our focus to one of the most profound challenges in modern physics, the quest to unify quantum mechanics and general relativity through the lens of quantum gravity. This theory isn't just about understanding the universe's smallest particles or its largest structures, it's about bridging the gap between them to reveal the true nature of space, time, and the universe's shape. Quantum gravity seeks to reconcile two seemingly incompatible frameworks. On one hand, general relativity describes the universe on a grand scale, explaining how massive objects like stars and galaxies warp space-time. On the other hand, quantum mechanics governs the behavior of particles at the tiniest scales, where the rules of classical physics break down the problem. These two theories don't play well together. General relativity treats space-time as smooth and continuous, while quantum mechanics suggests it's granular and unpredictable at the smallest levels. So, what does this mean for the universe's shape? Quantum gravity theories propose that space-time itself might have a fundamentally different structure than we currently imagine. Instead of being a smooth, unchanging fabric, space-time could be made up of tiny, discrete units like pixels on a screen. These units, often referred to as quantum foam, could create a dynamic, ever-shifting landscape at the smallest scales. One of the leading candidates for a quantum gravity theory is string theory, which suggests that the universe's fundamental building blocks aren't particles but tiny, vibrating strings. These strings exist in higher dimensional spaces, and their vibrations determine the properties of particles and forces we observe. If string theory is correct, it could mean that the universe's shape is far more complex than we've ever imagined, with hidden dimensions curled up so tightly that we can't detect them directly. Another approach is loop quantum gravity, which proposes that space-time is woven together from tiny loops. These loops form a network, creating a kind of fabric that gives rise to the universe's geometry. In this view, the universe's shape isn't fixed but evolves over time, with space-time itself emerging from the interactions of these loops. The implications of quantum gravity for the universe's shape are staggering. If space-time is granular or composed of loops, it could mean that the universe has a fundamentally different geometry at its core. For instance, the smooth curvature we observe on large scales might be an illusion, emerging from the chaotic quantum behavior at the smallest levels. This could also mean that the universe's expansion, its ultimate fate, and even the nature of black holes are governed by rules we're only beginning to uncover. But why does this matter? Understanding quantum gravity isn't just an academic exercise, it could revolutionize our understanding of the universe's origins and structure. For example, it might help us explain what happens at the center of a black hole, where the laws of physics as we know them break down. It could also shed light on the Big Bang itself, revealing whether the universe truly began from a singularity or if there's a deeper quantum-level explanation. As we explore these theories, we're not just piecing together the universe's shape, we're uncovering the very fabric of reality. Quantum gravity reminds us that the cosmos is far stranger and more intricate than we've ever imagined, and that the answers to some of our biggest questions might lie in the tiniest details. With quantum gravity offering such a radical perspective on the universe's shape, it's time to turn our attention to the challenges astronomers face in determining the true geometry of the cosmos. Now, as we venture into the realm of observational challenges, it's important to recognize that uncovering the universe's true shape isn't just a matter of theoretical brilliance. It's also a battle against the limits of our tools and technology. Astronomers face a host of obstacles when trying to map the cosmos, from the vast distances involved to the subtle signals that are often drowned out by cosmic noise. One of the biggest hurdles is the sheer scale of the universe. Light from distant galaxies takes billions of years to reach us, meaning we're essentially looking back in time. While this allows us to study the early universe, it also means that the data we collect is often incomplete or outdated. For example, the cosmic microwave background, or CMB, provides a snapshot of the universe when it was just 380,000 years old. But interpreting this ancient light to determine the universe's current shape is like trying to reconstruct a modern city using a blurry photograph from centuries ago. Another challenge lies in the precision of our instruments. Even the most advanced telescopes, like the James Webb Space Telescope, have limitations. They can only observe a fraction of the sky at any given time, and their resolution is constrained by the laws of physics. This means that subtle features in the universe's geometry, like tiny variations in the CMB or the faint distortions caused by gravitational lensing, can be incredibly difficult to detect. Then there's the issue of cosmic variance. Because we can only observe a finite portion of the universe, our measurements are subject to statistical uncertainties. Imagine trying to guess the shape of a puzzle when you've only seen a handful of its pieces. Without a complete picture, it's easy to misinterpret the data or draw incorrect conclusions about the universe's overall structure. Adding to these challenges is the presence of cosmic dust and other interstellar materials that can obscure our view. These particles scatter and absorb light, making it harder to observe distant objects clearly. Even more confounding are phenomena like dark energy and dark matter, which influence the universe's expansion and shape but remain invisible to our telescopes. Despite these obstacles, astronomers have made remarkable progress. Techniques like redshift surveys, which map the distribution of galaxies, and gravitational wave detection, which probes the ripples in space-time, are providing new insights into the universe's geometry. Yet, each breakthrough comes with its own set of questions, reminding us that the cosmos is full of mysteries waiting to be unraveled. As we push the boundaries of our observational capabilities, we're not just refining our understanding of the universe's shape, we're also confronting the limits of human ingenuity. The challenges we face today may seem daunting, but they also inspire us to innovate, to build better tools, and to ask deeper questions about the nature of reality. With these challenges in mind, let's turn our gaze toward the future, where new discoveries and technologies promise to shed even more light on the universe's true shape. As we look ahead to the future of cosmology, the possibilities for uncovering the universe's true shape are as vast as the cosmos itself. The next generation of telescopes and observatories, like the upcoming Nancy Grace Roman Space Telescope and the Extremely Large Telescope, are poised to revolutionize our understanding of the universe. These instruments will offer unprecedented resolution and sensitivity, allowing us to peer deeper into space and time than ever before. Imagine being able to map the universe's large-scale structure with such precision that we can finally determine whether it's flat, spherical, or something entirely unexpected. One of the most exciting prospects is the potential to detect gravitational waves from the earliest moments of the universe. These ripples in space-time, created by events like the Big Bang, could carry clues about the universe's initial geometry. By studying these waves, we might uncover evidence of cosmic inflation or even hints of extra dimensions, reshaping our understanding of the universe's shape and origins. Advancements in computational power and artificial intelligence will also play a crucial role. As we collect more data than ever before, sophisticated algorithms will help us sift through the noise to identify subtle patterns and anomalies. This could lead to breakthroughs in understanding phenomena like dark energy and dark matter, which currently elude our detection but profoundly influence the universe's expansion and structure. Yet, even with these advancements, some mysteries may remain stubbornly out of reach. For instance, the nature of the universe's topology, whether it's finite or infinite, simply connected or filled with loops, might require entirely new frameworks of thought. Theories like string theory and quantum gravity could provide the tools we need, but they also challenge our current understanding of space and time. And then there's the tantalizing possibility of discovering entirely new phenomena. What if the universe's shape is influenced by forces or dimensions we haven't even imagined yet? Or what if our universe is just one of many in a vast multiverse, each with its own unique geometry? These questions remind us that the cosmos is full of surprises, and every answer we find often leads to even more profound questions. As we stand on the brink of these future discoveries, one thing is certain: the journey to understand the universe's true shape is far from over. Each new tool, each new observation, and each new theory brings us closer to unraveling the mysteries of the cosmos. And while we may never have all the answers, the pursuit of knowledge itself is what drives us forward, inspiring awe and wonder at the infinite complexity of the universe. With that, we've reached the end of our exploration of 30 theories about the universe's true shape. From flat and spherical universes to holographic projections and cosmic bubbles, the diversity of ideas is as vast as the cosmos itself. If you've enjoyed this journey through the mysteries of space, don't forget to like, subscribe, and hit the notification bell for more mind-bending explorations. Until next time, keep looking up. The universe is waiting to reveal its secrets. As we wrap up this cosmic journey, it's clear that the universe's true shape is one of the most fascinating and complex mysteries in science. From the simplicity of a flat universe to the mind-bending possibilities of a holographic projection or a multiverse, the theories we've explored today showcase the incredible diversity of ideas that scientists have proposed. Each theory offers a unique lens through which we can try to understand the vast, intricate structure of the cosmos. What's truly remarkable is how these theories challenge our imagination and push the boundaries of what we thought was possible. Whether it's the idea of a torus-shaped universe looping back on itself or the concept of quantum foam churning at the smallest scales, each idea invites us to rethink our place in the grand scheme of things. And while we may not have all the answers yet, the pursuit of these questions is what makes cosmology so thrilling. So, what do you think? Do you lean toward the elegance of a flat universe, or does the idea of a spherical or hyperbolic shape spark your curiosity? Maybe you're captivated by the thought of our universe being just one bubble in a cosmic foam or a projection from a higher dimensional reality. Whatever your perspective, the beauty of science lies in the endless possibilities and the shared journey of discovery. If you've enjoyed diving into these theories with us, don't forget to share your thoughts in the comments below. Which theory resonates with you the most? And if you're hungry for more space mysteries, hit that subscribe button and ring the notification bell so you never miss an exploration into the wonders of the cosmos. Thanks for joining us on this journey through the universe's true shape. Keep looking up, and who knows what secrets we'll uncover next.